We are going to start talking about the first type of chi-squared test that we're going to use. We actually have two different tests that we're going to learn in this chapter. The first one here is called the chi-square test for independence. And so this says that a common use of the chi-square distribution is in this test for independence. And what this does is it involves using a contingency table. We've seen those before. This is basically a two-way table to determine whether two factors are independent or not. So we're going to have two variables of interest, and we're going to be comparing the distributions based on the two variables and see if it looks like they're independent or not. So I'm going to give you an example, kind of get your head thinking about what we're doing here. So this says consider the two variables, age and then political party affiliation. So we have one variable that we're asking our individuals that is referring to their age, and then another variable that we're asking to those same individuals, asking their political party affiliation. So you'll notice there's one group of individuals, we're collecting data on two different variables. If these two variables are independent, then for any value in age, right, or any group of age, the distribution of political party affiliation would look identical. So in other words, if we knew someone's age, it wouldn't tell us anything about his or her political party affiliation. That would mean that the variables were independent. If, however, the variables are dependent, what that would mean is that if we knew someone's age, that would tell us more information about their political party affiliation. Okay? And so that would be an example of a chi-squared independence test. So let's set up the null and alternative hypotheses in general first, and then we'll go into a specific example. So for an independence test, our null hypothesis is always going to be that the two variables are independent. And then our alternative, this is different from the alternatives we've done in the past. In the past, we've always had three different options for the alternative, but that is no longer the case here. We only have one choice, and that alternative is going to be that the two variables are not independent. Okay, so another way you could say that is that they are dependent. All right, so a little bit more information about these tests for independence, and then we'll go into our example. So first thing here is it says that the independence test is always right-tailed, and that again is because we're adding up sums, and so when we add up those quantities, we're going to get either zero or positive numbers. The degrees of freedom for the independence test, what we're going to do is we're going to take the number of columns in our for one of our variables. That's going to be basically the number of different outcomes for that variable, and subtract 1. And then we're going to multiply that by the number of rows, which again is basically the number of outcomes for that variable, minus 1. So we're going to multiply those together. You'll see us do that process in a second. The other thing that we need to know is something called the expected value for each of our cells here. And so the expected value for each cell is going to be calculated if we do it by hand using the row total times the column total divided by the grand total. We are going to use our calculator. And so it's going to do all that work actually for us. I'll show you how to do it by hand, but we'll do it on the calculator. And then we do have a requirement for the independence test, which is that the expected value for each cell being a block, a rectangle here in our table, needs to be 5 or greater in order to use the test. So let's get us into an example which will help us understand how to do this test a little bit better. We're going to stick with the age and political party affiliation data set. And so I gave you the setup before, but I did not give you the values of the variable and the number of observations we saw within each value. So here it says consider the data set below, providing the age. So we have ages over here. and political party affiliation, which is going to be up here, for a sample of 401 people. So that's our sample size. And we are asked, are the variables age and political party affiliation independent? And we're going to use a 5% significance level. So just to start off with here, our null hypothesis is going to be that age and political party affiliation are independent. That's always our null. And our alternative is going to be the age and political party affiliation are not independent. So I'm just going to age and political party affiliation are not independent. Okay, so we have our null and our alternative. We know that our significance level is 0.05. One thing that we would need to do is we would, you'll notice I put the observed values for each cell. I wrote them in there really small, and that's because usually if I'm doing this by hand, I divide each cell up so that I have a split here of my observed value and my expected value. The way that we would calculate those expected values for each cell is take the row total times the column total over the grand total. So let's look at this for a second. If we were going to take the total number of people in our sample that were aged 20 to 34, that would be the sum of this first row. So that would be 51 plus 38 plus 13. That ends up being 102. So I'm just going to put totals over here. The sum or the total for people aged 35 to 49 was 34 plus 39 plus 22. That's 95 people. Ages 50 to 64 ends up being 108 people. And ages 65 to 79 ends up being 96 people. We know, by the way, that there's a total of 401 people that were included in this study. If we do the same thing for our columns, the total number of Democrats that we found was 51 plus 34 plus 42 plus 40. That's 167. The total number of Republicans was 178. And the total number of independent voters is 56. Okay. The way that we are going to calculate the chi-squared test statistic is going to be taking the sum of the observed minus expected values squared over the expected. Okay. This is a long, slow process by hand. So what this means is for each cell in our table, we would first need to calculate the expected value. We do that, back up here, we do that by taking the row total times the column total over the grand total. So let's just I'll do maybe one or two of these. So let's start with the first cell. That's going to be Democrats between the ages of 20 and 34. If we know the observed value was 51, so there were 51 people that were observed that were Democrats and in that age group 20 to 34. If we wanted to know the expected value, so that's the expected value assuming that the null hypothesis is true and that age and political party affiliation are independent, the way we would find that is we would take the row total of 102, multiply that by the column total, which was 167, and then divide that by the grand total, which was 401. And you'll notice there we get 42.48 if we round to 2 decimal places. We could continue through that process finding expected value for every single one of our cells. I'm going to do the last one as well here. The last one has a row total of 96, a column total of 56, and we would divide by that total of 401, and we would get 13.41. But again, if we're doing this test by hand, we would have to find those expected values for every single cell. So all 4 times 3, right? All 12 cells. And then what we would do is we would take the observed value. 51 was what we observed. Expected for that first cell was 42.48. We would square it. We would divide by the expected, which was 42.48. And we would do this for all 12 cells. Adding them up through the last one, observed was 12, expected was 13.41, over expected was 13.41. So again, you can see that that ends up being a very long process. So we're gonna do it using the calculator. So if you go ahead and pull out your graphing calculators, the way we're gonna do this test is the first thing we have to do is we need to enter all of our data into the calculator. And because this is not a list of data, it's a two-way table, we actually need to enter it as a matrix. So on the left-hand side of your calculator, you'll see a button that says second, and then matrix. So we're gonna hit second, matrix. We're gonna scroll over with our arrow keys to edit matrix A. And the first thing we need to do is we need to tell the calculator the size of our matrix. So matrices are always sized by number of rows by the number of columns. And so we have 1, 2, 3, 4 rows and 1, 2, 3 columns. So this is a 4 by 3 matrix. So I just hit 4 by 3 and then hit enter. And now we're gonna enter in all of those observed values. We do not need to enter in the expected, just the observed. So we have 51, 38, 13, 34, 39, 22, 42, 57, 9, 40, 44, and 12. And so once we have our observed values there in matrix A, we are going to hit the stat key. We're gonna scroll over to tests, and we're gonna scroll down. We've used tests before, but this time we're gonna keep scrolling down until we get to option C here that says chi-squared test. And we're gonna hit enter. And you'll notice it's asking for your observed matrix. So as long as you typed your observed values into matrix A, you're all set there. Expected, you do not have to calculate those all by hand, so that would be these values, the 42.48 that we only calculated 2 of. You don't have to calculate those by hand, just skip that. It will calculate that matrix for you. And then hit enter on calculate, and it will find this chi-squared test statistic for you. So it ends up being 14.31. So again, if we had continued and did this all by hand, we would have gotten 14.31 with a p-value of 0.0263. And so at this point, we would want to compare that p-value with our alpha level. And so since 0.0263 is less than the p-value, less than the alpha value of 0.05, we are going to reject the null. So we are rejecting that age and political party affiliation are independent, and we are going to conclude the alternative, that they are not independent. In other words, knowing someone's age is going to affect their political party choice, all right? And so let's summarize this here with our conclusion, which is at the 5% significance level, the data provides sufficient evidence to conclude that age and political party affiliation are, you could either say not independent or you could say dependent. I'm going to say there is sufficient evidence to conclude that they are dependent, right? We rejected the null that they were independent.